All right, thanks for the introduction. As you can see, this is joint work with Dag Normann from the University of Oslo on some extensions of the Big Five. Actually, this is part one, real analysis. We do reverse math and computability theory of the uncountable. The first part, I'll talk about extensions of the Big Five. This is all on the archive. If you're interested, take a look. And the second part, I'll talk about metric and second countable spaces, mostly third order things. It's on the archive, and it will be, some of it is not on the archive yet. It's in my book. I wrote a book on reverse math, number 4 in the series, I guess. And so, it will be in that, which Springer, presumably. Now that I have your attention, so if you're going to remember anything at all, it should be this slide. So, I mean, it's all newspeak, but the conference is called New Paradigms and all that. So I thought, you know what, let's one slide for a new connection or a new paradigm. And if you're going to remember anything, it should be this. So how do we get our new paradigm or our new connection? Well, we start up there. So we start from axioms from set theory like countable choice, or Pfefferman's projection principle, or the enumeration principle. Hopefully you know countable choice from set theory. The enumeration principle just says countable sets can be enumerated, like in a sequence. And Pfefferman's projection principle, well, you know Pfefferman developed predicative mathematics most of his life. And in one of his papers he says, well, the projection principle gives you all relevant in predicative math. So it's a fairly strong axiom. You start with that. We'll get to that. So if you look at most textbooks, they never define enumeration except for trivial cases. They just give you an injection to n, or they show that it's a countable union of finite sets. So that is what countable set actually means, injection to n, or what I said. And an enumeration is a special, namely you are given an explicit list. And these are very different in the third order world, as we will see. This is actually a very strong principle. Like, its fragments imply ATR 0. One of many definitions, yes. So you can have lots of equivalences for these guys. So why not? Because it's reverse math. Countable choice, these things have many equivalences, and you work in, of course, in Kohlenbach's higher order system. And then you have all this pie in the sky, and then you want to make it more concrete. You want to push it down to second order reverse math, so you take restrictions. What restrictions? Effective versions of these function classes. Measurable functions you may have heard of, Baire 2, the Baire property, these are all well-known function classes. But the restrictions are to the effective versions. So function is Baire 2 if it's the limit of a sequence of Baire 1 functions, which means that for each function there is a sequence of continuous functions. Effectively, Baire 2 means there's a double sequence. Slight difference. And then these restrictions give you equivalences for these bigger systems. So pi11 comprehension and ATR 0, they're well known. They're second order, and they don't have that many equivalences. So these guys give you equivalences for those. And something new also for sigma 1 axiom of choice. So this is, if you're going to remember anything, remember this. You can take the higher order reverse math stuff and push it down to second order reverse math. Of course, the things, these are second order things, the equivalent things are third order. Yes? What? So measurable, one of the many definitions is the inverse image of an open set is an F sigma union measure zero set. How do you effectivize that? You just say, if I put in a reverse math open set, a code, then the inverse image should also be given by codes. So the codes for an F sigma, obvious, and codes for a measure zero function, let's say it's arithmetical. So that's what effective usually means. All these things can be written down via a definition involving inverse images. I mean, continuity can too. The inverse image of an open set is open. So the inverse image has to map reverse math codes to the right reverse math code. That's this. So this is everything, and we can now go to the pub, or we can also listen to me a little bit more. So yeah, I wrote the reverse math. It's in Reverse Math 2001. It's canonical. It's in the New Testament if you want. So the reason why Ulrich introduced this, he wasn't such a fan of the frugal language. We only have variables for naturals and sets of naturals. Things have to be represented or coded. This is messy, and usually now Steve Simpson already starts shouting at me, but he's not here. So this is the definition of continuous function. You show this to a non-logician, it's, like, where's the epsilon? I mean, somebody ran away, that's pretty strong. Pretty bad, I guess. But so it's not clear what this is to me as initially at first. So Kohlenbach uses the language of all finite types. So you have everything you could ever want. Third order is mostly enough. Like, I'll mostly be in third order. So yeah, you know, first and second order. Third order is just mappings from reals to reals. And sometimes we will use fourth order. I'll prepare you. I'll give a warning. There's almost no coding anymore, which is lovely. Like, you can directly talk about discontinuous functions. And this is how Kohlenbach got started. And I should say that the base theories prove the same second order sentences. So you might as well be working higher order. I do want to say a few words about this here. So yeah, type 0 is the natural numbers, type 1 is elements of the Baire space, and you just keep going up. Like type 2 is a mapping from the Baire space to n. You can have mappings from Baire space to Baire space, and so on. Now, Kohlenbach wrote things down in a very terse way. In my book, I have like a 60-page introduction on the base theory. But it's really, first of all, they prove the same second-order sentences. And it's really similar, like they both have primitive recursion and induction, of course. Then there's function extensionality. This is something you're not used to if you work second order. So here, for example, function extensionality means equal elements of the Baire space map to equal elements of the natural numbers. So equal inputs yield equal outputs. This axiom seems trivial, is rather important. Kohlenbach also included a little bit of choice. So for all there exists, then there's a choice function. But what does this do? Why did he include this? It's very simple, because it guarantees that second-order codes denote third-order functions. I'm not gonna reinvent the wheel. I want to use all this second-order stuff. And for example, if I have a total code for a continuous function, this formula expresses that code is total. And then I get this G, and from that I can define a third-order function that denotes the second-order code. So Kohlenbach included this not just for, there's a reason, namely exactly this. It also gives you delta 0, comprehension, but so what? This is the true reason. There's lots of work on coding, and we can just use that thanks to Mr. Quantify Free Axiom of Choice 1.0. So that's why it's included. And the real numbers, the real numbers are fast converging Cauchy sequences. Real equality is also exactly like in RCA 0. So we have the real numbers, and then, well, if we want to do real analysis, we want to talk about functions from reals to reals. Now, functions from reals to reals are just functions from Baire space to Baire space that respect this equality. So equal real numbers map to equal real numbers. And you will agree that this is not extremely advanced math yet. So this is all we need. The language includes mappings from Baire space to Baire space, and we should just have extensionality. And this is only a thing if you work below ACA 0. If you have ACA 0 or stronger, all this is automatic. Sometimes it's a bit pricey in weak systems. So the biggest five. Again, a story about Harvey, but for the pub later. The biggest five. Our starting point, if you know Ulrich Kohlenbach, you know that he can be very adamant. And so Ulrich was very adamant that we discuss the coding of continuous functions. But this is actually rather logically tame, as follows. If you have the base theory plus WKL0, any third order continuous function has a reverse math code. So, so I just need a function from reals to reals that happens to satisfy the epsilon delta definition of continuity. So Kleene, according to Dag Normann, who has met the guy, Kleene already knew that continuous functions can be coded. Ulrich Kohlenbach showed the case of Cantor space that it can be done in a weak system. Dag Normann essentially showed the case for the unit interval, and I proved much shorter but non-effective proofs. So that's how it is. And now you have to think about this for a second. Is your mind open? This is second order, and it proves something about the third order universe. We thought that's weird, and that's not the only example we have. Something second order, because this is just wall decoration, something second order proves something about the third order universe. And we started working with that. And then, this came out. So we realized that this can be done a lot. Like, there's a lot of equivalences between the second order big five and third order theorems about discontinuous functions. Usually slightly discontinuous functions, sometimes very discontinuous functions. But the point remains, there's a plethora of equivalences between second order and third order stuff. And that's what's going to be the biggest five, of course. So now the English language, or at least the American variety, has this modifier ish. Something is greenish if it's sort of green. Now these third order theorems, they're third order because, well, they are. But they're also sort of second order. They're second order-ish because they can be made equivalent to the big five. So, nice. And as far as I know, that doesn't happen for first and second order. First and second order are really different, also the theorems. But the next level, it's already sort of, there's not so clear, this is really third order. But why is it equivalent to second order? So, first and second order are really different. Second and third order already sort of mingle, apparently. So we'll start with an example, of course. So, because the big five, we have to pimp them to the biggest five. This is a second order. This is from Steve's book, mostly. Continuous functions on the unit interval is bounded. This is all code. And that's equivalent to WKL. So these are all known things, except for maybe Coussin's lemma. That's I'm going to write down for future reference. So Coussin's lemma is Heine-Borel. Before there was Heine-Borel. So the full lemma is as follows. For any psi that maps from the unit interval to the positive reals, so for any such psi, I mean, here it's restricted to continuous functions, but for any psi, there are reals such that the unit interval is covered by this finite subcover. So intuitively, psi to the positive reals gives you an uncountable covering, namely this one. So you have an uncountable covering, and that has a finite subcovering. That's Cousin's lemma. He proved this before Heine Borel, but yeah, nobody ever read his paper, I guess. So that's Cousin's lemma. He's French, I guess, sometimes mistaken for a Belgian. And yeah, Cousin's lemma for continuous functions is equivalent to RCA0. Now, you can also, the same equivalences you can get if you go to RCA0 omega and third order functions that are continuous. Not a surprise. But then you start thinking, yeah, but why restrict to continuity? There's no reason why we should restrict ourselves anymore to continuous functions, especially because, history lesson, especially for the Americans, Euler, Abel, Fourier, Dirichlet, they already studied discontinuous functions. Discontinuous functions were a thing before there was set theory, long before there was set theory. And yeah, so let's see what happens. So the following third order theorems are equivalent to WKL. Boom. A cat-like function is bounded, is Riemann integrable, a Baire 1 function has a sup if it's bounded, and so on. So these are exactly the same theorems. I just replaced continuous by larger function classes. And so regulated means that the left and the right limits exist. So Bourbaki somehow loves regulated functions, but it actually goes back to Gaston Darboux, 1870s. So people already looked at this back in the day. Cat-like is also a French word. Continu à droite, limite à gauche. It means regulated plus continuous on the right. So these functions are a big thing in stochastic, whatchamacallit. So this is not something fringe. Baire 1, yeah, function is Baire 1 if it's the pointwise limit of a sequence of continuous functions. Baire 1 is very well behaved, apparently. I have semi-continuity. So Baire, in his thesis, studied semi-continuity. And I should write down the definition. So upper semi-continuous, or USCO. So F, we talk about the unit interval, is USCO at some real number if for any epsilon, because, well, it's sort of continuous, there is some natural number. For all epsilon, there's a delta if you want. For every y in this ball, f of y is below f of x plus epsilon. It's 1/2 of the definition of continuity. And yeah, that's semi-continuity. It's, yeah, if a function is, there's also the lower version, if it's both, it's continuous. So this is also well studied, even in PDEs, for example, this comes up. Villani, Fields medalist, has a whole book on this sort of thing. Then there's also quasi-continuity, which is rather interesting. So Volterra, name you should ring a bell. Volterra identified quasi-continuity first, and Baire even says at one point, no, I didn't come up with that, it was Volterra. So I'm writing this down because I'm going to refer back to it, of course. So F is quasi-continuous at x. it's also epsilon delta. If for all epsilon, and for every natural number, go for type 0. There is some interval, AB, where the continuity stuff happens. So it's not continuity, but there's an interval AB always where the continuity magic happens. That's why it's quasi-continuous. So you always have this interval. It doesn't matter if it's open, half open, or closed. And in this interval, you have the usual epsilon. It's quasi-continuous. A function from the plane to the reals that is continuous in each coordinate may not be continuous, but it's always quasi-continuous. That was the observation by Volterra and Baire. So now, later, we realized there's a lot of quasi-continuous functions. If you believe in that sort of thing, there are 2 to the power of the continuum non-measurable functions that are quasi-continuous, and 2 to the power of the continuum non-Borel bounded and measurable quasi-continuous functions. So how many continuous functions are there really? A little less. So we little WKL is equivalent to theorems about rather crazy function classes. And yeah, I love this. It's beautiful. So, and that's the first example. Let's look at ACA 0. So here are a couple of things from the literature. The first 2 are from Steve's book. And then André Nice and the gang have looked at the Jordan decomposition theorem, restricted to codes of continuous functions. Sure, it's equivalent. Why not? And again, why do we restrict to continuity? Because let's look at the third order stuff. So again, we can replace continuity by cat-like. If there's a cat-like function on a reverse math closed set, the supremum exists, and so on. And so yeah, we can, again, cat-like and quasi-continuity come up. And so this is a massive generalization, in a sense. Again, cat-like means continuous on the right, limit on the left. The thing from stochastic analysis. And these are just examples. There's many more function classes. This we can. Let's just skip right ahead to ATR 0 and their third order theorems equivalent to ATR 0. So if we go up a little bit, so the Jordan decomposition theorem for functions with an arithmetical or a sigma 1,1 graph, or effectively Baire 2. If a set has an arithmetical definition and a limit point, we have ATR 0, and Cousin's lemma for effectively Baire 2. So that's the psi there, right? The psi you limit to effectively Baire 2. Sure, again, just examples. And I want to make the following clear. Baire 1 means, pointwise limit of a sequence of continuous functions. Baire 2 means that it's the pointwise limit of Baire 1 functions. So these are Baire 1 functions. So there exists a representation. We're not given this representation. It's a Baire 1 function. There exists a sequence of continuous functions that converges to it. Effectively, Baire 2 means that it's actually a double sequence of continuous functions. This is how people code Baire 2 functions. But so there's a fundamental difference between Baire 2 and effectively Baire 2. And we need effectively Baire 2 here. And actually, Baire himself, so being Belgian, we are predisposed to speaking more languages. One can read Baire. If one reads French, you can read Baire. And he says this literally at the end of a chapter. You know what? Baire 2 functions can be represented as the double limit of polynomials. Ils peuvent être représentés. So even Baire was saying, well, they can be represented. He made a distinction there. Of course, I don't think he had this in mind, but still. Pi-1-1 comprehension. So I should say two things. So here we have X. Sometimes you have to extend your base theory. X is usually induction. I hate induction. So we just throw it in there whenever we need it. So, and also we work over a slightly stronger system that has been mentioned already. So AC 0 omega. AC 0 omega is just RCA 0 omega plus E2. And E2 is, yeah, arithmetical comprehension. It expresses that there's some functional E that decides if function has a 0 or not. So E of f outputs 0. So yeah, it's arithmetical comprehension because you can replace an arithmetical formula by a quantifier free one. So that's E2. And it's L2 conservative over ACA 0, as shown by James Hunter in his thesis. James Hunter was kind enough to allow me to put his proofs in the appendix of my book. So, yeah, with streamlined notation, etc. But so, yeah, this is the base theory we often use because it's convenient. So Dag Normann and I don't always go for the weakest base theory. Call us lazy Scandinavians if you want. But so, this is just an example, but yeah, if you somehow define sets with a sigma 1-1 definition, that's a class actually, it has a sup. And effectively, Baire 2 function has a sup, and actually for any effectively Baire n. So a Baire n, effectively Baire n function is just an n double sequence of continuous functions. And you take the successive limits n times. Yeah, so I should say, again, there's a difference between Baire 2 and effectively Baire 2. And this is the start of the biggest five. The second order big five are equivalent to many third order theorems. These are just a nice selection. There's many more. How many? In my book, I used the alphabet for a theorem about boundedness, and I ran out. So after 26, of course, what do I do? A, B, C to Z. So one can do Z1, Z2, Z3. Just to say there's many equivalences because every function class gives you a new variation. For the Americans, those are metric gazillions. But so it's obscene how many function classes there are, and each function class gives you a new theorem if you want. So yeah, we have a massive extension of the big five, and we call it the biggest five. And yeah, this is in Journal of Mathematical Logic if you want to take a peek. But this is only half of the story. So I want to talk about mathematical versus logical proximity. And in particular, what I write here, second-orderish theorems can be mathematically close to non-second-orderish theorems, but logically far apart. What do I mean by that? This. So the Jordan decomposition theorem restricted to quasi-continuous functions. So yeah, if you have quasi-continuous functions, that's ACA 0. Sure, right? But here comes a very closely related theorem. The Jordan decomposition theorem related to cliquish functions, which is not provable from full Z2 and stronger systems. So they're logically far apart because this guy is provable in ACA 0. This guy cannot be proved from full Z2 and stronger, higher order, bigger, better, faster systems. Now, what does cliquish mean? Well, first of all, every cliquish function is the sum of two quasi-continuous functions on the reals. So they seem closely related because, well, one is just the sum of two of the others. Secondly, the definitions are similar. So the definition of quasi-continuous we have. And this is the definition of cliquage. So for every epsilon, for every n, for every x, there is this interval such that the function values clique together. That's why it's cliquishness. But note that they don't clique around f of x necessarily. But if anybody does not see why these two definitions are very similar, let them speak now or forever hold their peace. So these, even if you don't believe in intuitive statements, as some people here don't, I know, but these definitions are similar. People say that in mathematics. Like there's a paper, somebody tried to cram something in between. So in between these two notions is simple continuity. And this was, wow, this is good, people said, because these two definitions are very similar, they're very close, but you can still cram a function class in there. So these two are mathematically close, but the theorems are logically far apart. This is just one example. Here's another one. A pi11 comprehension is equivalent to an effectively Baire2 function has a sup. Sure. That's pi11 comprehension. Full Z2 cannot prove that a Baire2 function has a sup. And they're the same thing over ZF. Effectively Baire and effectively Baire2 are the same in ZF. You don't need choice to prove that. Yet, here the definitions once more. Yet this guy is provable in pi11 comprehension. This guy, full Z2 plus a lot more, doesn't prove it. So again, these are mathematically close. Well, actually, they're the same thing mathematically, but logically far apart. Again, this is an important observation, and it has nothing to do with the axiom of choice, because ZF proves that a Baire2 function is effectively Baire2. Some guy named Elliot Glaser proved that on Math Overflow, I guess. Yeah. It's similar to what people call codes for Baire2 function. Because you have a double sequence of continuous functions, but yeah, they're not given by reverse math codes, they're just continuous functions. So they're third order. So, because we don't, I personally do not push stuff down to the second order world. Yeah. Yeah. There's one master sequence, yeah. Exactly. But that's what I said on the first slide, isn't it? No, that is true. So this is actually, in a sense, more natural than that, definitely. So the effective part that pushes things down from high up to pi11. That's what's happening, indeed. Not always, but here. So like the other cases, yeah, there is no coding. It's just quasi-continuous and cliquage. There is no coding. But in this case, indeed, the coding pushes it down. I stand by that. So one last example, because this is where it gets confusing, and this is where I was confused. So a bounded Baire1 function has a sup. That's just equivalent to WKL0. The proof isn't easy. The proof, like, I usually leave the difficult proofs to Dag, and he managed, but this is not easy. So in case you think this is all just, fingers up the nose. So an upper semi-continuous function that has a sup, that's not provable in Z2. Now this is annoying because, Baire1 means that, upper semi-continuity is there. Semi-continuous functions are Baire1. So that's annoying, but this is apparently very hard to prove. So in a weak system, the function classes can be very different. You can't prove that a semi-continuous function is Baire 1. And actually, yeah, theorems about Baire 1 are weak. Theorems about USCO functions are strong. And yeah, so people still say that semi-continuous and Baire 1 functions are close or similar. But there's a big difference. So I mean, if you think about it for a moment, you have the entire hierarchy of all function classes. No, you can't prove that that happens in RCA0. It's just not possible. But here, even in strong systems, you can't find this Baire 1 representation. Yeah, that's how it is. And yeah, Yokoyama-san bolted already. But so they use codes for semi-continuous functions that hard code the Baire 1 representation. I'll let you be the judge of what that means. I think my opinion is clear. Effectively Baire 2.
The omega square sequence.
Yeah.
Continuous functions.
Yeah. Elliot Glaser proved that. Difficult. It's all math overflow. Take a look. It's not a trivial proof. It's like transfinite recursion. It's not easy, but ZF can do it. So now, so I keep talking about myself and Dag Normann, but one should be fair here. All this rests on Kohlenbach's early reverse math of Kleini's E2. So you need the reverse math of discontinuous functions because it's around the corner everywhere. So in my book, I start with that, of course. So, for example, E2 is equivalent to the existence of a discontinuous function. This is Kohlenbach essentially implementing Grigliot's trick inside a weak system. But you can have many equivalences, like there's a function that is not regulated because, well, that would be discontinuous. But also, the composition of regulated functions need not be regulated, for example. And this is what people do in real analysis, because we know that the continuous functions are closed under composition, and most other classes aren't. So there's this, they do it in Würzburg, or used to do it in Würzburg where Anton is. So composition operators, when can we compose and where does that go? Well, that's equivalent to E2 often. So yeah, there is a function that is not semi-continuous, or yeah, composition of semi-continuous function need not be semi-continuous. A function that is not Riemann integrable, a function that is not Baire 1, a function that is not Baire 2, effectively Baire 2. Boom. There is a function that is not Baire 2, then you can't prove in fairly strong systems. So here also you get this phenomenon. Eventually you run into a wall. Like Baire 2, for example, is the wall you run into. Like, I have my cool equivalences, and then it stops. And the difference is something. E2 is at the level of ACA 0, and this you can't do in Z2 and stronger systems. Even you can add some choice to that. Countable choice you can add, still doesn't work. So the biggest five phenomenon is just that. Second order big five equivalent to third order theorems, but slight generalizations of second orderish theorems are not provable from full Z2. So that's why we call it the biggest five, not just the bigger five. So we have lots of equivalences, and we know that it stops somewhere. There's a hard wall we run into. Slight generalizations is where we get something that's far beyond the big five, like in the case of effectively Baire 2 versus Baire 2. So that is the biggest five. And yeah, again, the name is inspired by Harvey Friedman. And you may wonder, why do we see this phenomenon? Why are there the biggest five, and why are there these variations that go way past the big five? Why do we observe the aforementioned phenomenon? I can tell you. So you know that continuous functions are nice. And why are they nice? Because, for example, it's actually a third order object, but we only need this second order object to perfectly describe it. The graph of a continuous function is determined by this, the values on a countable dense subset. That's, of course, why coding works, right? All essential properties are equivalent to arithmetical, like this. If there's an x that exceeds, f of x exceeds y, then there's a rational. So that's how you get the supremum, because you can, in ACA 0 or something, because you can replace this quantifier by a rational quantifier. It's obvious. Now comes something non-obvious, which you may not have known. There are a lot of discontinuous function classes with that very same property. So here we have them. Like Baire 1, quasi-continuous, and so on. They have both properties. The function values are already determined by a countable dense subset, and we have this kind of thing. Any formula is equivalent to an arithmetical one because of the countable dense subset. And it may not always be arithmetical, it might sometimes be sigma 1, 1. But this is the point. People in reverse math have this irrational fear of discontinuous functions, but there's lots of nice ones that behave exactly like the continuous functions. Namely, this. And what is weak continuity? So there's this AMS code, 58 something. It's called weak continuity and generalized continuity. So people study weak and generalized continuity. There's many definitions. For most of those, they're similarly nice. They have these properties. They're determined by, say, their behavior on the rationals, and as a result, everything is arithmetical. There's also classes of discontinuous functions that don't have these properties. And one is simply false for basic counterexamples. So that's an important point. So they don't have these properties, and there's basic counterexamples. Often it's Dirichlet's function. So here, regulated bounded variation again, a couple of weak continuity notions, like 7. So they don't have these properties, and one is simply false. So this is what I wanted to tell you, and these nice classes can be studied in the Big Five. So get over your initial irrational fear of discontinuous functions. There is lots of nice discontinuous functions which can be studied with the Big Five. And then, of course, there's these guys which can't be. And unfortunately, Yokoyama-san et al., they chose these guys. And André Nice and the gang, they chose bounded variation, and they made codes, and it's, a mess. So these are also the ones that can be coded nicely. And these you shouldn't try to code. And this is what's going on. So when you hear discontinuous function, there's nice ones that won't bite. Of course, there are those that do bite. And I should say something about the axiom of choice, because it does play a role here. It's actually very interesting. So before there was Heine-Borel, there was local global. So this strapping gentleman is called Salvatore Pincherle, if I pronounce that correctly. All right, Pincherle. So he proved what is called his theorem. A locally bounded function on a compact set is bounded. Locally bounded means there's a little ball where it's bounded. And he didn't use the word compact, of course, but that's essentially what he was talking about. So he, when he was young, he went to see Weierstrasse and his circus in Berlin, and came back to Italy and brought these new ideas. Let's look at the proof by contradiction of this theorem based on the axiom of choice. So this is local global because, it's a local property implies a global property. And this actually predates compactness. Let's look at the proof by contradiction, and here we shall use this kind of axiom of choice. So it's essentially countable choice for quantifier-free formulas. It's not provable in ZF. So how do we prove this? Well, suppose not. Suppose f is locally bounded but not bounded, so f is unbounded. We apply countable choice to this formula. So for all n, there's an x where f of x exceeds n. Sure. Apply countable choice, you get a sequence. And then we use sequential compactness on the resulting sequence. So this sequence has a convergent subsequence. And then we observe f is not locally bounded at the limit because, yeah, it has to become arbitrarily large. So this is a trivial proof, but it's also very deep. Because intuitively, we cannot remove the red quantifier. We cannot remove it in favor of an arithmetical quantifier. So we really need something here. For example, countable choice. We need this guy because locally bounded gives you no information. It's actually a very, very wide class. And so let's make that less intuitive. Well, let's make that more concrete. So Dag and I proved in our 5th paper, if you have countable choice, Pinkerless theorem is equivalent to WKL0, as it should be. Z2 little omega cannot prove Pinkerless theorem, and Z2 big omega can. Now, what are these mysterious systems? So, Z2 big omega was mentioned, is RCA 0 omega plus Kleini's E3. E3 decides a lot more than E2. So you take as input a third order object, and it can decide if there's an element of the Cantor space, the Baire space. So it can remove quantifiers over the Baire space. It's a very powerful axiom, and it's L2 conservative over Z2, as shown by James Hunter in his thesis. The Z2 omega does not have choice really, but it does prove Pinkerless theorem. So we have a proof. We can choose either we use Z2 big omega or we use WKL and countable choice. I would choose the first one. There's also Z2 little omega. The lesser system is RCA 0 omega plus the union of all S2K. I'm not going to write down what that means, but S2K decides I1K formulas, sentences. Why not formulas? Why not formulas? We can have parameters in their Kleini normal form. So this is also L2 conservative over Z2. This guy cannot prove Pinkerless theorem, and the big guy can. For reasons we do not understand fully, but that's what happens. So this thing is at the level of full second order arithmetic if we don't have choice. So yeah, if that, we don't need the axiom of choice, but things are a lot prettier. So countable choice does seem essential if we want a nice reverse math picture. And I'm totally into aesthetics, as you can see by my dress. So well, let's just assume countable choice whenever we need it. And this is Pinkerless theorem is the first theorem chronologically and the first theorem that we studied. So there's many other theorems that behave as in A and B. So we call this the Pinkerless phenomenon. So you have a lot of situations where if you have countable choice, the reverse math works out nicely. If you don't have countable choice, it's ugly as sin. So yeah, let's just assume countable choice as a base theory, even for the biggest 5 sometimes. But countable choice is yeah. You can also look at fragments of countable choice, that works, but we just assume it, boom, because somebody else can fill out the details if they want. So, yes, and countable choice actually has interesting reverse math, which we will discuss later. All right, so that was the biggest 5, and I'm going to say something about the bigger 5, and then we'll have a break. So the bigger 5, so what was the biggest 5 again? Lots of equivalences between second order big 5 and third order theorems. Of course, a lot of third order theorems are not provable from the big 5 and even Z2. And even this guy, by the way, like this guy doesn't prove the following. So here are 4 nice systems that cannot be proved here. Z2 omega plus a lot of choice cannot prove these 4. The uncountability of the reals, Jodoh decomposition, the full theorem, Baire category, and Tao's pigeonhole principle for measure. So these are the bigger 5. I call them big systems because they boast many equivalences. That's chapter 3 in my book. So the biggest 5 is chapter 2. Chapter 1 is introduction and all hail Kohlenbach. Chapter 3 is about the bigger 5. These guys, they boast many equivalences. And they're like I mean, come on, the uncountability of the reals. Which boy's dream isn't it to reverse the uncountability of the reals, you know? I know it was mine. And now I've succeeded. Right, now let's start somewhere. So, a very rare moment of self-criticism. So, definitions matter greatly according to Simpson. So, this quote is from Subsystems of Second Order Arithmetic. So, essentially, Simpson was saying, we started off with Dedekind cuts. Whoops, that doesn't work. Let's use fast converging Cauchy sequences. Now it works. Thank you, Ian. So the initial definition of real number wasn't the right one. So this is very important in reverse math. You have 20 equivalent definitions. Which one do you choose that works in RCA 0 or RCA omega? That's the point. And people make mistakes. That can happen. But this also happened in constructive math, like Waldeck and Bridges discovered that, whoops, the definition of continuous function in constructive math is wonky. Let's change it and, yeah, never talk about this again. So it's not unique to reverse math that you choose the wrong definition from all the many equivalent definitions. So this happened in constructive math, and yeah, those who forget history, etc., you know, are poised to repeat it. So now I told you this boy wants to reverse the uncountability of the reals so much. What is the right definition of countable set, of course, as was foreseen by Alberto? So actually, what's a set? Because I haven't said that really. I've said, yeah, there's functions. But so we're going to be a bit lazy here. We're just going to assume ACA 0 omega. So we assume clean is E2. And then a set is just given by some characteristic function. And the characteristic function, of course, is what you know, 0 and 1. So we assume characteristic functions. Those are the ways we represent sets. And this is possible because we assume E2. So sets are just given by characteristic functions. You know what functions are, you know what sets are. We can go below AC 0 omega, but I don't want to go into this detail. There's a book out there, I hear, soon, so please take a look there. But so generally, if you see set, it's a characteristic function, and yeah, we don't want to bother with all these technical details, you know? We'd never get anywhere. So let's reverse the uncountability of the reals. So if you look at real analysis, it's about functions from reals to reals, and these sets are crucial. The set of points where f is continuous, and the set of points where f is discontinuous. Good, right? Why not? Now, if we have a regulated function, so regulated function is sort of the outer ranges of Fourier analysis. So yeah, Fourier, it's everywhere in goddamn physics, engineering, etc. So this has been very well explored, and yeah, even regulated functions, so you only have left and right limits, they can only have countably many points of discontinuity. Right? The set is countable, but even very strong systems, like this guy, even strong systems cannot prove that there's an injection from df to n. So yeah, that sucks. And yeah, now what? So this is just a sign that injection to n is not the right definition for reverse math. What is the right definition? Actually something very close. This is the right definition. We can easily prove that df is always height countable, and height countable means that there's a height function. What does this mean? It just means that an injection maps any element to a unique natural. The height function maps finitely many to one natural. So I call it height countable because, yeah, I need a different name. Height countable, so height functions, Borel discusses this in like in his book with Dag, and it's in a couple of papers. So height functions, I didn't invent this, this already exists. It's also found in the literature. People never define an injection, they define a height function, like for the rationals. You can sort of see it before your eyes, right? So height countable means union over n of finite sets, and apparently in the literature on the axiom of choice, this is called CUF, C-U-F, countable union of finite sets. It's not such a crazy idea. We don't use injections, we use height functions or unions of finite sets. That's what we do. And then you start reversing, and success. If you have this notion, you get a lot of equivalences. And boy, did I try. If you use injections to n, you get one equivalence. I mean, maybe it's my inability to reverse, but so I only found one reverse math equivalence that's nice when using injections. You really have to use height countability. That's the right definition, in the same way that the right definition of real number is fast converging Cauchy sequences in reverse math. So the right definition is height countable, or CUF, as the set theorists are wont to call it. That's that. And so let's have some equivalences. The unit interval obviously is not height countable, it's not CUF, it's not a union of finite sets. And this is equivalent to a regulated function is not totally discontinuous. But there's at least one point where it is continuous. That's a very weak statement, but we can make it weaker. We can even say quasi-continuous here. Volterra's theorem for regulated functions. So there is no regulated function that's continuous on the rationals and discontinuous on the irrationals. Here, Riemann integral. So we have a regulated function. The Riemann integral exists and is zero. Then, well, at least somewhere we have to have a zero. This is a special case from a theorem by Bourbaki. The fundamental theorem of calculus, because why not? The fundamental theorem of calculus is equivalent to the uncountability of the reals. This boy is happy. So, and only at one point. So we assume that the primitive exists, And then we can differentiate it and we get the original value back. Those are equivalent. And yeah, there's too many variations, again, by my book. And this is all close to or related to Fourier analysis. We can also do this for Fourier analysis, like a function of Banach variation. There's at least one point where the Fourier series converges to the function value. Why not? So the sky is the limit, but I'll give you one proof now. It's not that difficult. So to show the downward direction, so, well, it's easy to prove that the discontinuity set is height countable. It's actually the textbook proof. Because it's height countable, it doesn't equal the unit interval by item A, and so there's a continuity point. That's, of course, you still have to define DF and CF, but that's why you have E2 here. So these sets exist, no worries. This is easy, this is just the textbook proof. The reversal turns out to be rather textbook too. So we have a sequence of finite sets of reals, and we have to show that the union is not the unit interval. But to do so, we define this function. H of x is 0 otherwise, 1 over 2 to the n, if x is in xn and n is the least. We can define this function. Again, we need E2. We observe that it's regulated, so it has a continuity point by item B. And it has to be 0 there by continuity. And so it's not in this union, and therefore the unit interval does not equal this union. And essentially that's how you prove all these theorems with variations. So I happened across this function after the fact. So Meyerson, an analyst, I guess, he published this paper in the AMS Monthly about Baire 1 functions, and he uses exactly this function to prove sort of equivalences between definitions of Baire 1. I was happy. So this function appears in the literature, and you always modify it a little bit, but this is the core of the matter. I thought that was cute. It's from the literature, and this made Harvey Friedman sway. He used to be burn higher order reverse math. Now you don't have to burn it. There was some back and forth on the FOM a while ago. You may have seen. So, almost there for lunch, for coffee break, gentlemen. Because, yeah, there's only gentlemen here, I guess. Yeah, wait, can I finish this one? Yeah. So, I wanted to say, there are people who publish papers like 10 proofs of the uncountability of the reals, 10 different proofs of the uncountability of the reals. And so many third-order theorems actually imply that there's no injection from the unit interval to n. Or even that there's no injection that is also surjective, so a bijection. It's difficult to get one but not the other. And so NBI was suggested by Carl Mummert and Jeff Hurst. And yeah, it's hard to prove. So even if you have Z2 big omega, you cannot prove that the reals are uncountable. But it's weak. If you add it to ACA 0 omega, it's just ACA 0. Alex Kreutzer studied the Lebesgue measure and follows from his results. You can restrict to nice functions from R to Q. It can be regulated, can be USCO. So NIN is equivalent to restrictions of NIN to regulated functions. Z2 cannot prove NBI, but countable choice can. So that's something. And these are essentially the weakest natural third-order theorems that are hard to prove. So this is kind of a Swiss Army knife. If you want to know if something is not provable, then you try to derive NIN or NBI. So the advantage is, as I said, people really publish papers like 10 different proofs of the uncountability of the reals. So you have a lot to start with. So this is stronger than the uncountability of the reals. A height countable set can be enumerated. And it's explosive. Maybe we should have a coffee break then, or yeah, all right. All right, coffee break time.